So when I thought about what topic I would talk about, I thought about the need for speed, the main thrust of that project. And of course, one of the stumbling blocks of software development is always testing, software testing. And one of the reasons it's a stumbling block is that it's in large part manual in most environments. So I decided I would talk about how to automate in a scalable and effective way software testing. And what I will argue is that test automation needs to be driven by models. And this is not a new idea. This has been researched for a couple of decades. Some companies are selling products, including one in Finland. And I'll talk about that. But it's not yet part of mainstream practice. And therefore, this is what I will discuss. I will try to discuss about the challenges and provide guidelines. So I don't know what's going on with the slides. It's all the formatting is gone. We might have some surprises along the way. Something is happening with the formatting here. I might have to use my computer if it gets bad. Okay? Sorry for this. So I will try to summarize about 20 years of experience in trying to cost-effectively automate testing. I will try to explain why automated testing driven by models is the right way to go. And we refer to that usually as model-based testing. It's not always possible in every circumstances, but it's, I believe, the right way to go in most situations. And I will show, more importantly, why and how to tailor model-based testing to a given context. What are the factors that you have to take into account? Because model-based testing doesn't come in one shape or form. In fact, there is quite a bit of tailoring to do in order to make it successful. But I will spend most of my time going through some project examples, because the best way to communicate ideas is through examples. Examples of projects that I've run recently with companies back in Luxembourg. So first, let me tell you where I'm coming from, because very few people know what Luxembourg is, even in Europe. So it's that tiny country stuck between Belgium, Germany, and France, with 3 official languages, despite its size. 50% of the population is foreign, so that makes it already quite special. And for some reason, they decided about 8 years ago that ICT security and reliability was going to be a national priority. And as a result, they created the center that I'm working for now, the S&T Center, which has grown quite a bit in the last 5 years. We also host a number of headquarters of well-known IT companies such as Amazon, PayPal, Skype, and also automotive companies such as Goodyear and Delphi. The S&T Center was established in 2009 as a result of that national strategy of developing activity in the area of ICT security and trust. And since 2009, we have grown to 230 scientists, and we have 23 industry partners working with us in the satellite, automotive, banking domains, and others. In my case, I'm in charge of a lab focusing on software verification and validation. And I work with 6 industry partners in the satellite, automotive, banking domains, among other things. In terms of what we cover, the type of expertises we cover, we range from requirements engineering, including quality assurance, to automated software testing, including testing for embedded software, security, and data-intensive systems. So, in fact, the way we work, the paradigm of research we follow, is very similar to what Need for Speed is trying to establish here. And that's why I thought it was extremely interesting for me to come here and try to share your experiences. We try to run research projects in such a way that research is driven by innovation needs in concrete contexts. As you may know, far too much research is taking place in a vacuum. Researchers in their offices, disconnected from the real world. And we organize our partnerships in such a way that we develop the research problems we work on in close collaboration with our industry partners. And the goal is not only to produce research that leads to publications, which of course is necessary in a research environment, but also serve an existing market. And the way we do that is that we follow a quite standard and systematic process in our research collaborations, where we carefully define the problem we work with and reformulate it into scientific terms and into sub-problems that we can tackle in a stepwise manner. And then eventually we identify the gaps between the state of the art and the needs, and of course devise alternative solutions and go through a number of validation steps with our partners. And all the projects I will show as examples here today were basically run according to that paradigm and methodology. So let me get back to basic terminology just to make sure we have a common understanding here. So by testing, I mean the process, any process that consists in executing software with the intent of finding and correcting defects. Ideally, we would like that process to be systematic and automated, and I'll get back to that. But there are two types of testing that people are talking about, and I will show examples of both. One is testing before deployment, what people typically refer as testing, integration testing, system testing, acceptance testing. But sometimes the term testing is used to refer to something else. That is testing after deployment, which is also referred to as runtime monitoring and verification, or test in use. That is when the system is deployed. As we know, most of our systems, of course not yours, is buggy when deployed. So what can you do to at least avoid catastrophes, to avoid serious damage? And again, sometimes people refer to that as testing, online testing, test in use. There are many terms, and I'll show an example of that. So, testing is standardized. There is an ISO IEC standard, which mostly consists in defining concepts, terminology, processes. But of course, what the standard doesn't do is to tell you how to automate testing, how to make it cost effective. And so this is what I'll be talking about today. Before we talk about automation, we need to identify what needs to be automated. So that's what I'm going to talk about now. Well, when you test a system, obviously you need some form of test inputs. What those inputs are depend on the type of testing you are performing. You need test drivers, that is program that execute the software under test. That software under test may not, in most cases, execute in isolation. So it needs to be able to interact with sometimes what people call stubs, software stubs, that emulate, for example, the environment, or that emulate an external system the system under test is supposed to interact with. And eventually, of course, that system produces outputs, which can be of different nature, depending on the system. And somehow, a mechanism must be in place to decide whether or not a test case passes or fails. And of course, when we talk about test automation, we need to determine how we want to automate the generation of those artifacts. So what are the test automation needs then? We need some way of generating test cases, ideally. We need some way of automatically generating a test oracle. That is something that will automatically determine whether a test case passes or fails. We need possibly some test stub generation. We need something, an automated way of emulating what the software under test interacts with in order to be able to automate testing. We, of course, need some way of automating test execution, some way of logging and analysis test results. And we need, and this is something that very often people forget, ways of handling test suite evolution. That is, how do we deal with, for example, requirements changes? Assuming you have thousands of test cases, a requirements change, what do you do with your test suites? How do you handle evolution? And in practice, and of course there are exceptions, there are a few companies who tend to support many of those items, but in practice, most of the testing tools that are being sold only address those 2 points. And of course, the problem is that this has consequences, it has dire consequences. Test automation is not scalable, it's expensive, though, as I often say, the cost of testing and the cost of non-quality is often hidden in most organizations, so it's not quantified, which of course is convenient for the people involved, you know. Testing is error-prone, it's not systematic, and it's not predictable. So let's look into those items. So why isn't it scalable? Well, because you have to deal with hundreds or thousands, in most cases, of test cases that you have to define. Basically, you have to write the test scripts, and you have to maintain them when requirements are changing, for example. Then it's expensive, because people time is expensive in our society. The main cost of software development is people. And even more of a problem is that, as we all know, it's true in Luxembourg, it's true in Germany, it's true in France, it's true in Finland. Competent people are hard to find in IT. So wasting the time of competent IT engineers is a bad idea. It's error-prone. Why? Because people are really terrible at performing lengthy manual and repetitive tasks. They hate it, and they don't do a good job. So if you tell people, write scripts for hundreds of test cases and update them when there is a requirements change, chances are they are not going to do a very good job at it. And it's not systematic, because what happens is that when you run out of resources, when you run out of time, you take shortcuts. So as a result, your testing, when it's manual, is unlikely to be systematic. And what that means when testing is not systematic is that it's not predictable. You cannot rely on what you have done in previous projects to decide whether your test strategy is adequate or not, because no systematic test strategy was used in previous projects. So, I told you I was going to try to convince you that model-based testing was the way to automate testing, and that I was going to discuss about challenges and provide practical guidelines based on experience. But in model-based testing, you have the word models. Most of you here probably know what I'm referring to, but it's still a short refresher should not hurt. So a model in software engineering is any abstract or analyzable, and the term analyzable is important, description of software artifacts. And those models are created for a purpose. As you know, there are many modeling standards that exist that are supported by commercial tools, including the UML, SysML, which is a profile of the UML, MARTE, another profile of the UML for real-time embedded systems, BPNN for information systems that basically run business processes. And the idea is that models here are used and analyzed, in our case, in order to drive test automation. That is, in order to address all the automation requirements that I've listed in my previous slides. And in fact, it should not come as a surprise. Modeling should not come as a surprise, even though it's not yet a widely spread practice. It's a feature of any engineering discipline. That's the way engineers in all engineering disciplines deal with complexity. And modeling in software engineering is used more particularly in certain application domains, like automotive and aerospace, and government also in some cases, I'll show you. And as we will see, it's a key to scalable automated testing. That's what enables, of course, model-based testing. But the way you do modeling, like the way you do model-based testing, is going to be driven by the application domain, standards and practices in place, the objectives of testing, and the skills that people have. So there will not be a one solution fit for all in terms of test automation. That won't exist. So what is the model-based testing process? And we are going to see a lot of examples that are going to follow that process. The test engineer, the analyst, has a mental model of what the system should do. That mental model of what the system should do is somehow captured in a model, an explicit model, an analyzable model of the system and possibly the environment of the system. Especially, for example, in the case of embedded systems, the environment also must be part of the equation. Then, based on that, the idea is that once this is done, everything else is automated. The generation of test suite and test scripts, test stubs, oracles, and also test objectives can be carefully defined so that you know when testing is completed. Because this is also another issue for test engineers, is that they never know when their job is done, basically. Well, it's done when the deadline is up, but that's not a very satisfactory way of working. And eventually you get test results that are being analyzed in order to determine whether a failure may be due to a mistake in the model, and in that case you go back and correct the model, or whether some additional testing objectives are needed because, for example, a large part of your system was not covered, and obviously something was missing in your model. A functionality was not covered by your testing, for example. But that's, at a high level, the process for model-based testing. And of course, one of the issues of implementing model-based testing is diversity. The diversity of systems you are dealing with. Those are systems I've worked on in the past 10 years, example systems. And obviously, the way you implement model-based testing in a recycling machine or in a medical image segmentation software or in automotive software or a payment system is not going to be the same, obviously. You cannot expect test automation to work the same way for all of those systems, and I'll show you why. So in the past 5 years, I've worked on many projects related to test automation in many, many different domains with very different objectives, ranging from safety to robustness to CPU usage, using different notations, though in many cases we used extensions of UML, and with many underlying technologies for automation. So the lessons learned I will draw will come from all those projects. But of course, I will only show you a small subset of projects. Okay? So the first example is with a large American company called Delphi, an automotive system supplier. As you know, the amount of software on electrical control units is constantly increasing and getting more complex. Software is controlling injection, braking, cruise control. I mean, many, many parts of the car. And that increase in complexity, of course, poses increasingly also testing problems, as you can imagine. One critical part of the software running on electrical control units are controllers, usually dynamic continuous controllers, that control devices of any kind. And those controllers are complex because they don't have only discrete behavior, they also have continuous behavior, because they are handling physical parts, obviously. So their behavior cannot be only discrete, which is the type of software usually people develop and test. And for example, controllers in a car control the engine, the injection, the braking system, that's what they do. And the way automotive software is developed and controllers are developed is usually through 3 stages. You have a model in the loop stage, and usually in this industry, like in others, people tend to use MATLAB Simulink. So Simulink is a modeling language which is geared towards control engineering, though people have used it for other reasons as well. And it's a graphical language, a data flow language, which can be simulated. So what people do here in the first phase, they develop their controllers with Simulink, and they develop models of the environment being controlled with Simulink, which means that they are able to execute the system without hardware in the loop. And of course, this makes testing much cheaper, as you can imagine. And a great deal of the testing is taking place here. Therefore, a great deal of the testing is already model-based. Okay? Eventually, software is being generated, though the environment is still modeled and simulated. And eventually, the software is running on actual hardware or physical simulators. And this is the hardware in the loop stage. But as you can imagine, testing is very expensive here in the hardware in the loop stage. Only relatively few test cases can be executed because it's manual to a large extent. You have to set up the hardware before running a test case. Usually it's largely manual. And of course, the test cases can damage the hardware. Certain situations cannot be simulated, as you can imagine. So testing is extremely difficult and expensive here, which means most of the bugs must be found here. And in fact, what those guys are doing is already model-based testing, except that it's not very systematic. And that's where we came in and we tried to make it more cost-effective and more systematic. And so let me focus on model-in-the-loop testing. So this is the ultimate goal of model-in-the-loop testing, is to ensure that individual functions behave correctly and timely on any hardware configuration. So in order to explain what testing controller means, I need to tell you a bit about controllers. Controllers, during the model-in-the-loop stage, the mill stage, interact with models of the plant, or plant models, which in other words, this is a term they use for models of the environment. Whatever is being controlled, okay? It can be a valve, it can be any kind of physical device. And what happens is that the controller sends output signals to the plant model, then the environment state changes, something happens, the valve is changing position, for example. The information about the state of the plant is getting back to the controller, which then computes new output signals to be sent to the plant. Okay? And that's how all closed-loop controllers at least work. Now, when you test controllers, what are you testing for? When you want to automate testing, the first question you have to ask is, what am I looking for? What type of faults am I looking for? In this case, controllers being what they are, there are three main properties. Liveliness, which is basically whether or not if the red line is your target position, the blue line is your actual position over time, is whether you actually reach your target position within a certain level of precision. Smoothness is whether you reach it without too many turbulences, without too many bumps. Why? Because when there are bumps, it damages the hardware. So you want to converge smoothly toward the target position. Last, you have responsiveness. Do you reach the target position fast enough? Of course, time is essential here, you can imagine. So when we test controllers, we are looking for violations of liveliness, smoothness, and responsiveness requirements. First, we have to define requirements, and then we are looking for violations of those requirements. And the question is, how do we do that in an automated, cost-effective manner? And I'm not going to go into a lot of details, but I'm going to give you a glimpse of how we do it. How we do it is that you have the input space, and here I'm simplifying the problem. The input space here is just only consists of the final desired position and the initial desired position. For example, the position of a valve. You can imagine a valve, that's a simple example, that has to move, okay? And what we do is that we use search algorithms, effective search algorithms, to find high-risk areas, which are depicted in red here. And once we found them, we use different type of algorithms to actually find violations. And here is an example of a violation, for example, where you have the initial desired position, the final desired position, and here, as you can see, there is a large bump before converging to the final desired position. This is an actual example of a bug in a controller. And so here we rely basically on what we call meta-heuristic search algorithms coming from artificial intelligence, where we have ways of guiding the search in the input space towards higher risk areas. And the only way this can be automated is because we have Simulink models. Without the Simulink models, none of this would be possible, because we would be stuck with hardware in the loop. Okay? Here you can run those search overnight. You can run that on high-performance computers with 2,000 nodes. Doesn't matter. There is no hardware in the loop. There is no human in the loop. And here is another example, and this time I'm talking about online testing or runtime monitoring. So it's not testing before deployment, it's testing after deployment. Okay? And this is a project with the computing center of the Luxembourg government. It's a small country, so there is one computing center that develops all e-government applications. And what is runtime monitoring or runtime verification? So you have development, you have specifications of some kind. Your code is instrumented, or you use a wrapper or a proxy. The code itself doesn't need to be instrumented. There are different ways of doing that. And what happens is that after deployment, that program, the proxy or the instrumented program, sends a stream of events to a runtime checker, which basically is in charge of checking at runtime specifications. That's, in 5 seconds, what runtime verification is. Of course, the devil is in the details, as you can imagine. So what do you need to be able to apply runtime verification or online testing? You need a specification language, which is domain-specific, something that enables people to easily express the properties in their domain with the least effort possible. A mechanism to generate execution traces. If you would want to do runtime verification, you need to collect information about the execution of the system, obviously. And usually those are called execution traces. And you need a runtime checker, which with a minimum impact on the monitored system, and that is efficient at runtime, is analyzing those traces and detecting violations of the properties you have specified. So example of properties in an actual system I worked on with the Luxembourg government. It was an identity card management system. I'm not getting into details, but it was a special type of ID cards. Let's put it that way. And for example, here are 3 examples of properties that needed to be complied with by the system. Important properties. Once a card request is approved, the applicant is notified within 3 days. This notification has to occur before the production of the card is started. The applicant has to show up within 5 days from the notification to get a personal data collected. If the applicant does not show up within 5 days after the second notification, the request will be denied and the applicant notified about the refusal. So as you can see, those properties are properties of business processes. That's what they are. And also they are temporal. There are a lot of temporal properties embedded, as you can see. Okay? And in this particular context, actually, the Government Computing Center is modeling all their e-government applications with business process models. So here we get back to models. That's what they do. And those business process models originally were meant to be used for contractors, to be able to tell contractors exactly what they wanted, and then to drive the acceptance testing once the system was delivered. So every e-government application was modeled in terms of business processes. And as I told you, there are standards for that. The BPMN comes to mind, and that's what they did. And basically, the properties I've shown before are properties that can be expressed in terms of the business process model in a very accurate fashion. And in their case, they actually have a modeling methodology. They already basically use modeling as part of their development methodology, far beyond just doing business process modeling. They use different things that are listed here. And basically for us, performing model-based testing meant to rely on business process models. That was, of course, the natural thing. So in the previous example, we relied on Simulink models. Here, we relied on business process models. And of course, that's natural. Here, we are talking about e-government systems. Before, we are talking about controllers. You know, the type of properties, the practices, everything is different. So here, just quickly, the status of that project is that we have defined a domain-specific language for business process properties called CLR. We translate it to a standard constraint language called the object constraint language, for which there are constraint verification engines that are mature and quick that exist, Eclipse-based engines, for example. And so what we do is that we translate those high-level properties into low-level properties that can be checked on those constraint engines. And what we do is that we check basically traces for properties. We have done a lot of performance analysis in order to make sure that our implementation had acceptable performance. In the context of runtime monitoring, performance is the main challenge. Your algorithms, your constraint verification algorithms have to be tuned to achieve performance. The devil is in the details. Okay? Another example, again, completely different. And you remember that the goal for me of showing those examples is to show you the variety of implementations of test automation and model-based testing, so that you understand all the factors that come into play. And I'll get back to that, of course, at the end of the presentation. So this is another company that develops sensor systems. And an example of sensor system, which is quite simple, but they develop more complex ones, is the system that determines the occupancy in a car. Who is sitting in a car? Is that a child? Is that an adult? You know. So, and of course, as you can imagine, that occupancy system is used for different reasons. It's used for controlling the airbags. It's used for various number of reasons. So here, what is the problem? Again, completely different from the two previous examples. Here, in that context, people adopted use case-driven development. Everything about the system is captured as use case specifications. Those use case specifications are used to interact with the customer, of course, which has to approve them, but in addition, they drive the entire development process. Incremental development is performed one use case at a time. Use cases are the center of everything. And again, you know, there are reasons why people do what they do, and you have to account for the practice that is in place when you want to implement test automation. Another requirement, because this is the system I've shown before, is an automotive system, so it has to comply with a standard that, among other things, lists a number of requirements for functional safety, which is very common in most embedded systems, in most industries. Everybody has his own standards, but they are quite similar. That standard says that all requirements should be tested. All test cases should be traced back to the requirement then, and managing test cases and traceability manually, in that case, of course, is not an option. You can imagine if you have thousands of test cases, hundreds of use cases, you're not going to manage traceability entirely manually. Of course you can, but you know what the consequences are going to be. Errors all over the place, expensive traceability analysis, expensive change management, you know, etc., etc. So for us, we need to achieve those first that requirement here about requirements traceability, but we wanted to do it in a cost-effective manner. And basically, we had to have we had to define a strategy to go automatically from requirements to test cases according to a systematic strategy and in a fully automated way. And we needed to capture traces between requirement and test cases for certification purposes and for change management purposes as well. So what we did is that for each use case, of course, use case specifications were defined. This was already part of their practice. But we decided that, well, okay, we are not going to change the practice. this is what they did, this is what they do. They write use case specifications, detailed use case specifications that are used to interact with the customers. And this was a constraint we had to work with. But we decided to change the way use cases were written so that they were more structured, they were more restricted, that is, people had less degrees of freedom, so that those use case specifications could be, could be analyzed. Could be analyzed using natural language processing, techniques for analyzing natural language. And why do that? To eventually, as I will show you, derive in a stepwise manner test cases from use case specifications. And of course, you cannot do that if people have total freedom when writing use case specifications. If anything can be done, then it becomes unanalyzable, and therefore automation is not possible. But of course, we had to do this in such a way that the customer could still easily read and understand the use case specifications. We could not come up with a very formal model that would be beyond the reach of the customers. The use case specification had to be legible for customers. But at the same time, they had to be analyzable for test automation. So we came up with a specific use case specification methodology that enabled analysis and eventually test automation. And more specifically, here were the model-based testing steps. We had the use case specification. We call that restricted use case modeling. It's our methodology, our specific methodology for use case specification modeling. Of course, there were a few other inputs that were required. I won't go into details, but basically we needed to define all the concepts that were part of the system. For example, the type of errors, diagnosis, because this is a sensor system, devices that were controlled by the system. We needed a domain model, in other words, in addition to the use case model. And based on that, we generated an intermediate test model, that is an intermediate representation of all the use case specifications that enable transformation into test scenarios or abstract test cases, and eventually transformation into concrete test cases, that is test scripts, on the specific deployment platform of that system. And all this was only possible because use case specifications were analyzable to start with. We could derive an intermediate test model that then enabled full test automation. Basically, the main enemy of test automation is ambiguity, as you can imagine. So when use case specifications are not developed according to a precise analyzable form, then ambiguity sets in and automated testing becomes very difficult. Here is another example. I think the last one I'll go through, depending on the time. Again, completely different domain. As you will see, completely different solution. This is a satellite domain, and it's a specific type of system in the satellite domain called data acquisition system. That is all the system that gather and analyze the input stream from the satellites. And this is one of the European leading companies in the satellite domain. So here is what the data acquisition system is, for those who are not familiar. It's a system that gets input transmission from the satellite, and here the data that are transmitted are very structured and very complex. Of course, this is not a unique feature of data acquisition systems, but many other data-intensive systems have that feature, based on a number of configurations that tells the system about what to expect about the data being transmitted. That system generates log files, for example, capturing possible errors in the transmission input. And of course, the main goal is to extract data from what is being transmitted by the satellite. And when people were testing this, it was mostly manual. Why? Because what is testing here? Testing here means generating those large input transmission files. Very complex, very structured, with possible errors in them, because they are transmission errors, in order to test the robustness of the data acquisition system. And how do you want to automate this? a priori. I mean, it's not obvious at all. And testing was very expensive because those files are very large and complex. Many possible errors can happen during transmission. So many possible test scenarios can come to mind. And then there was a problem, of course, the oracle problem, the test oracle problem. How to decide whether test cases passed or failed. I mean, as you can imagine, analyzing that type of data to decide whether a test case passed or failed is not exactly easy, straightforward. We're talking about large amounts of data. So it's a bit like finding a needle in a haystack, you know. So what we did to automate that process, the model-based testing strategy we adopted can be briefly described as follows. We modeled the structure and content of the input transmission file, of the configuration file, and of the output file, and we modeled the relationship between those files as constraints. So constraint between what is present in an input transmission file, and as a result, what should be present in the output log files, for example. So we basically modeled the structure and content of the files and their relationships. And you have to do that once. And from that, basically, we derive two things. We derive an oracle mechanism, which is based on constraint checking. So basically, we took field data that existed for the system under test, and we generated test inputs by mutating or changing the field data, by introducing errors, for example, according to a typical fault model of the type of faults that happen in satellite transmission. And we, of course, ran the software under test, the data acquisition system, with those inputs. And basically, we compared the inputs and the outputs using the constraints we had defined before, that I've discussed before. And we use a constraint checking engine to do that and automatically detect inconsistencies between the input files and the output files. So basically, once the models were defined, those models, anything else was entirely automated. We automatically generated erroneous input files, transmission files, automatically checked whether the output was correct or consistent according to the constraints that were defined. And that was it. And we could run it all night using all the computing power at our disposal. It didn't matter because there was no human intervention and there was no hardware in the loop. So it's what we did, basically. I guess I don't need to go through that. But testing was entirely automated. And of course, it applies to all, that strategy would apply to any kind of data-intensive system, where the complexity is in the data, not so much in the behavior. Here's another example, but I think I'll skip that one. In a completely different domain again, real-time systems in different domains. A completely different strategy for model-based testing, but I'll skip that. And I'll go straight to lessons learned. So you have seen examples. Okay, so what? That's a good question, so what? So there are a number of questions that are interesting I want to go through with you. One is, what kind of models need to be developed to support automated testing? How expensive is modeling? What are technologies enabling automated testing based on models? How cost-effective is model-based testing? What are the limitations of model-based testing? And what are the open issues regarding model-based testing on which research and innovation are still needed? Obviously, those are questions you could have asked me, and I will spare you that effort by going straight to them. So what kind of models? Well, here I'm not going to be very precise, unfortunately, because when you talk first about what kind of models, you talk about two things. The notation, what modeling notation you use. As I've told you, there are many standards, extensions of the UML, SysML, MARTE, BPMN, etc. And there is a modeling methodology. And those are two different things. The modeling methodology tells you what is the scope of modeling, let's say, what is the part of a modeling notation you need to use, and at what level of detail you should go. And a notation is not enough. You need a methodology. You need to know exactly what is expected in your models. The standards exist, which means that you can use open source tools or even commercial tools. For example, now there is an open source tool that is really getting to maturity and around which an industry consortium is being formed called Papyrus. And it's an open source modeling tool. So you don't even need necessarily to use any of the commercial ones. And what is going to be the notation and the modeling methodology you should use in a specific context will depend on your test objectives. What are the targeted faults? The context, the domain, the type of system, for example. And also the existing practice and the modeling skills. For example, in the case of the IE example, the occupancy sensor system I've shown before. Their current practice was basically driven by use case modeling. We were not going to change that. There was no point to try to change that. So we had to account for existing practice. In terms of the domain and type of system, for the data acquisition system, as you have seen, all the complexity was in the structure and the content of the data, in input and the data being produced. So obviously, the focus of modeling had to be on the structure and the content of the data. Okay? So you see, there isn't one solution fit for all. All those factors play a role in determining what is the right test automation strategy based on models. How expensive is modeling? Again, this is hard to answer because it varies from context to context. And of course, it depends on the size of the system being tested. In my experience, it varies from a few days to a few weeks, depending on the context. What is important is that the test models on which testing or test automation is based must be much simpler than the system they purport to model. Otherwise, it's not economically viable. Okay? So ideally, those models should be much, much simpler than the system they model. Those models can also serve to other purposes. Obviously, models are usually extremely useful, for example, to train new people coming on board who don't know anything. And their colleagues are busy, they already have tight deadlines, so that's always a problem. It can be used, of course, for communication among different teams. For example, the example with the IE company, the one developing the occupancy system, their test team is in China. So you have guys in Luxembourg designing the system, and you have a test team in China. Communication is not exactly easy for many reasons. All those use case specifications were actually one of the main reasons why they existed was not just for interacting with customers. It was also for interacting with their test team in China. The real question, though, is not how expensive modeling is how much do you save in terms of test automation? That's the real question we need to ask. And here, in my experience, there is no question that in most cases you save a great deal. And it's not very difficult to save when testing is manual or largely manual. What kind of technologies are required? I haven't gone into details, but there is a machinery below. You don't achieve test automation without a somewhat complex machinery, automation machinery below, which usually involves things like constraint solvers, mathematical optimization, or meta-heuristic search, such as genetic algorithms. And it's okay, people who know about test automation and know how to handle those technologies. But the main challenge, of course, is always scalability. That's always the main challenge. Can you generate test cases within a reasonable time, automatically, for example? Now, of course, as I told you, model-based testing is not new. There has been a lot of research. There are even commercial tools. 3 of the ones I know are here. One of them actually, I think, originates from Finland, Conformic. Certify-IT, which is a tool developed by Smart Testing, and Matello, a tool developed by a company called All4Tech. Of course, those tools are a very significant step forward. In many ways, they're very good. But the difficulty is to understand what type of model-based testing technology you need, given your context and your objectives. And even those tools do very different things. For example, their modeling methodology or their underlying modeling methodologies are very different. This one is probably more geared towards embedded safety critical system. While this one, for example, is probably more geared towards information systems implementing business process models. You see? And then, of course, whether you want to use a commercial tool or develop your own technology, you have to ask yourself questions. You have to take, given your targeted domain, given the modeling notation that is adequate for that domain, given your test strategy, given the type of automated support you need, then you need to make decisions. It's not obvious. It's possible to choose a wrong tool that doesn't fit your context, and then to be unsuccessful at automating testing. So it's not obvious to make that choice. How cost-effective is model-based testing? Well, when you talk about cost-effectiveness, you have positive factors and negative factors. What does cost money? Well, modeling, training, and tools cost money, though you can use open source tools, like Papyrus, for example. And then there is the modeling overhead itself, the act of modeling a system and/or its environment. And what are the benefits? What are the savings? Well, test automation, obviously. Especially when you are dealing with hundreds or thousands of test cases, if test script and test oracles are generated automatically, I mean, that's definitely a huge source of savings. And regeneration of test suite when there are changes. This is another thing. If the generation of test cases and test oracles is automated, and there is a change, you regenerate. There is no need to analyze hundreds or thousands of test scripts to find out which ones are obsolete, which ones need to be changed, which one needs to be re-executed. This can be automated. And we all know that change is a main cost factor in most software development. Even in embedded critical software, change is overwhelming. Customers change their mind all the time. Yeah. Of course, another advantage is that your testing is more systematic and you have more confidence in what you do. And it's not just you have more confidence, but if you are in a domain where you need to be, your delivery needs to be approved by the customer, or even worse, approved by a third-party certifier, like in the automotive industry, in the oil and gas industry, in the aerospace industry, and many others, then it's very important to be able to tell people exactly how you tested your system, according to which strategy. You must have perfect traceability. If you don't have that, then getting your delivery approved is going to be difficult. So traceability is key also for impact analysis. I haven't talked much about that. I haven't talked much about regression testing, but obviously regression testing is very important. So what you would like, of course, is when there is a change, is not to rerun all test cases that are still valid. You want to know which ones need to be rerun and which ones don't. And that type of traceability that comes with model-based testing is very handy for that. So based on that, of course, cost benefits results vary according to these factors. There isn't a general answer, because what you lose or gain through this depends very much on context. But those are the factors you have to account for when you make the decision to implement model-based testing. My experience across the projects I've shown, and many other projects before that I had shown in that big table, is that the benefits usually far outweigh the costs, especially when accounting for changes. That is, there are benefits the first time around you test the system, but the real benefits kick in when you have many versions over time with many changes, and you need to retest and retest and retest and retest. Then model-based testing becomes a clear winner over half manual testing. And usually, I have also frequently asked questions that I get. So it's always good to go through that. What if the model is incomplete or incorrect? Obviously, modeling is a human activity. You can help it, you can support it, but it's a modeling activity. So models may be incomplete or incorrect. But it's important to remember that the purpose of model-based testing is automation, not proof. You want to automate a process that is largely manual, which means some failures may be due to mistakes in the model. You may have to correct the model, but it's okay. Eventually, your model is going to converge towards a stable, correct model. And most of the testing will be automated. Does ABT give me a proven test strategy? No, it doesn't, but you can define one. You have to define one that matches your needs in your domain and that matches your test budget. Without a model, you cannot even define a strategy. Based on what? Counting the number of statements you cover in your testing, this is meaningless. It's mostly meaningless. Except when a large part of your system is not covered, of course. But coverage is not a guarantee of anything. And as I said, there is no such thing as a universal proven test strategy. You have to adapt it to your context. Can I just buy and apply some commercial MBT tool? Perhaps, but it's not obvious. First, the choice of the tool is not obvious, and usually that will imply a lot of tailoring to your context. Isn't MBT too expensive to introduce and tailor to our needs? Well, it's not free, but manual testing is much more expensive and less effective. So it's a choice. Not making a decision, sticking with the current largely manual testing practices comes at a cost and with a risk as well. So not deciding is deciding. And one more thing too is that when testing is largely manual, it's very hard to retain talented people. People leave. They don't want to do that. They're not interested in supporting manual testing. At least the people who are clever and know the domain. They want to do other things with their lives. But when you transform those people into test automation engineers, as opposed to people in charge of performing manual testing, all of a sudden their job becomes much more interesting. They use sophisticated technologies, they do modeling. So model-based testing is also a way to retain your most talented test engineers. And we forgot very often that aspect. So now let me conclude, and I'm on time. Thank you, it's very useful actually. So there is a lot of hype out there. It's not just hype, but there is a large proportion of hype. You know, I don't want to use words that are going to offend anybody in the room, but you know, you hear a lot of fads about testing, you know. And every 5 years, the fads are changing. But the fads are changing, but the problems remain the same. Decade after decade, the problems are the same. We haven't solved them. We haven't solved, in many cases, how to do cost-effectively model test case generation, how to deal with automated test records, for example, how to deal with traceability, how to deal with change impact analysis. And, you know, decade after decade, we surf on a new fad, and we conveniently forget to address what are the core problems. Model-based testing is a technology that can address, not all the time, but in most contexts, that can address those core problems. It doesn't come for free. It requires investigation and decision-making, but it has reached now a level of maturity where it's feasible. Of course, model-based testing is a natural fit for model-driven companies that use or have adopted a model-driven engineering development methodology. But even for those who haven't, model-based testing is a good starting point, actually, for model-driven engineering. And maybe the most important message I want to convey today is that model-based testing in most contexts is in fact the only way to achieve test automation. I cannot think of any other way of generating test cases according to a systematic and cost-effective test strategy, generating oracle mechanisms to detect automatically failures. I don't know how to do this without model-based testing in most contexts. So the choice is not really whether to adopt model-based testing or not. The choice is whether to automate testing or not, to really automate testing. I'm not talking about automating test execution. or the logging of test results. I'm talking about modeling or automating the entire set of test activities. Of course, even though model-based testing is quite mature, there is still some degree of investigation that is required, some degree of research innovation that is required in a given context, because as I said, no two contexts are unique. But nevertheless, I think for most companies now, it's a cost-effective alternative to largely manual testing. Thank you.